What's going on, you guys? So today we're going to do count and say. So we've got this sequence of numbers, and we're going to give this function count and say, say the first, say we want the first count and say, or the second, or third, fourth, fifth, basically any number between 1 and 30. So if we say we want the first count and say, we give it 1. If we say we want the second count and say, we give it 1, 1. And here's why. So when you see the number 1, think about what you say. There is 1, 1. You say, so here, so first case 1, what do you say? So there's the number and then there's what you say. So I say 1, 1. Right? And so that could be interpreted as 2 1s. And so that's why we get, for the second one, we get 1, 1. Then for the third, you say the previous one. So for number 3, we're going to say 2. So I see 2 1s. 2 1s. And this is going to be 2, 1. And so that's why for the third we have 2, 1. So now how do we say 2, 1? We say 1, 1, 2, 1, 1. And this equals 1, 2, 1, 1. And that's what we get for the fourth. So now let's say the fifth. So 1, 1, 1, 2, 2 1s. So this equals 1, 1, 1, 2, 2, 1. Okay, and so on and so forth, all the way up to 30. So you take the idea here, and so we can already see that there's a recursive solution here. You take the previous. So if we say n equals 30, we take n equals 29, and figure out what is being said for n equals 29, and that will be the result for n equals 30. So let's think about some pseudocode here. Okay, so we have the base case. So if n is 1, we're just going to return 1. Okay, let's think about how we're going to do this otherwise. So if we're thinking about doing this recursively, which does have a space cost, because the call stack, our program's call stack is going to fill up with recursive calls. So that's the cost of a recursive solution. But sometimes the recursive solution is a little bit easier to understand. So it's a good place to start. And then you can make adaptations to improve the space complexity if you want. So we'll say our string, we'll say previous equals count and say n minus 1. So the previous number. And so now we have the previous one. We want to count the number of times each number occurs, append the count, and append the digit. And do that for the whole thing. And that should be our result. So we'll have a result. Let's start it with, let's think here. Okay, let's think. We'll come back to that. So what are we going to do here? Okay, so for I in, let's say current equals, let's set result equal to 1 and say current let's also say current equals 1 because that's the base case. Okay, let's think here. Current equals Yeah, okay. So for I in 1, so let's think about this. How are we going to do it for this one? Okay. For I in 1 until previous dot length. So we're going to loop over all the indices starting at 1 because we're going to take zeros. Oh, that's not necessarily correct. We can't say, because for example 3, the first number is 2. It's not always going to be 1. Okay. We're going to say current equals previous 0. So the first index, right? So that could be 0, it could be 1. Okay, so what are we going to do? We're going to say if current equals previous of I, starting at 1. So let's do this one. Let's walk through this one so it makes a little bit more sense. So I is going to start at 1. Okay. And so current is going to be okay, current is 1, previous I is 1, so we're going to increment a count. Okay, so we need to have a count. So let's declare count and set it equal to 1. Or if it's not equal, we're going to, let's think here, what are we going to do? Say result equals an empty string. We're going to say result. Oops. We're going to append. So let's go through this in our example. So, okay, so I is 1, count plus plus, count equals 2. So now I is going to move up 1. Okay, I equals 2, and current 1 equals 1. So count is now going to be 3. So now I is going to move up 1. Count is 3, and current does not equal 1 does not equal 2 in this case. So now what are we going to do? We're going to say result plus equals string of count plus string of current. So count is 3, so we're going to append 3, 3, 1. 3, 1. Result 3, 1 so far. Okay, what next? Then we're going to reset count. Say count equals 1, and current equals previous of I. So I is now 0, 1, 2, 3. 0, 3. So current is now going to equal 2. Okay? So we're going to go back through our loop. Current which equals 2 equals previous. Oh, and let's see. I is moving up 1. Okay. So current equals previous of I. True. So count plus plus. So count is now 2. Now we go through the loop again. And let's see. Current does not equal previous I. So now we're going to append string of count, which is 2, plus string of current, which is 2. Okay. Okay. And now we're left with the final value that we haven't appended. Now we're gonna set count equal to 1, set current equal to previous at I, and so we'll do one final append to handle the last value, and then we'll return result. So what's the final append gonna be? We're gonna append count is so count is gonna be 1 because we reset it, and current is the last value. Oh wait, let's think here. 1 1. Okay, right. Okay, so this should be the next value after 1 1 1 2 2 1. 3 1s, 2 2s, 1 1. Yeah, it sounds right to me. All right, so let's try and convert this to, wait, let's think about what's space and time complexity. So space and time complexity, time complexity. So we go through the length of previous. So O of string length. So let's call this S. S is string length. And we need to we're calling count and say, so say we call count and say 5, then we need to call count and say 4, then we need to call count and say 3, call and say 2, count and say 1. So it's string length times the number of times n, S times n. And what's the space complexity? So we're calling count and say n times, so it's n, and we're using some constant values. With a little bit of there's going to be a little bit of a kind of a gotcha in Java/Kotlin that I'll show you. So it might be a little bit more, but basically we're going to say O of S times n for time complexity, and O of n for space complexity because of the recursive function calls. Okay, so let's try and convert this to Kotlin. Okay. All right. The pseudocode is basically Python. It looks very similar. So you might ask, why don't you just do it in Python? It's a good point to make. I think it does help you go fast if you understand, if you can just keep in your head what the types are of everything. But using something like Kotlin, it allows you to keep track of what am I using here? Is this a number? Is this a string? Is this an array? So that's why I like to use the strongly typed language. And Kotlin, it's not so verbose like Java. So it's pretty similar to Python, minus like the var statements, and it does have some brackets. Okay, let's think here. Add one there. Anything else to change? All right, let's see if this works. Oh, oops. Okay, so we need to change this up. Let's just copy and paste this. Let's see if that works. Huh. Oh. Looks like we're missing a closing bracket there. Okay. Okay, there you go, guys. That's the recursive solution to count and say. So there's a few things about this answer that we could improve on. We could, for example, we could add a hash map so that we're not recomputing count and say every single time. So we'll only compute our first 5 values once. So we could do something like if count and say n-1, if n-1 is in the cache, then just return that value. And if not, then you can go calculate it. So that would be one improvement, is that would reduce the stack size calls from, it wouldn't be O of n every time. It would be O of n the first time, but subsequent calls would just be O of 1, because it would just be accessing the cache. What else? So in Java, strings are immutable immutable classes. So every time we do here plus equals string, it's creating a new string instance. And so that increases the memory requirement. So we can replace this with string builder. And that gets rid of that error where so every time you create so in Java, strings are immutable. So every time we do plus equals there, it's creating a new string instance. So that adds a bunch of objects onto the memory. So by doing a string builder, we're getting rid of that issue. So let's see if we can get this memory down. And then at the end, we'll just return to string. Okay. Let's see what that does. So a little bit better in terms of memory. 1 megabyte of memory, a little bit better. What else? Yeah, so the cache is probably the biggest thing. Because it takes the memory, O of n calls to count and say to just, the 6th time you call it, or the 2nd time you call count and say 4. It's just going to pull it from the cache. I'll leave that as an exercise for you guys, but stay tuned for the next one.